Welcome, everyone. Thanks so much for joining us today. We're going to wait just a minute or so for folks to come on before starting today's webinar. Welcome, everyone who's joining the webinar today. Thank you so much for your time. We will get started in just a few moments to allow others to join. All right, wonderful. Let's get started. Thanks again for joining. This webinar series is entitled Conversations on Ocean Carbon, a U.S. West Coast and Alaska Perspective. And it's co-hosted by the California Current Acidification Network, the Alaska Ocean Acidification Network, and the California Ocean Science Trust, with the aim to deliver the best available information on marine carbon dioxide removal and to explore concepts related to coastal ocean carbon. Thanks to those of you who have joined us for our first 3 webinars in 2023. The recordings can be found on YouTube, and we're excited to kick off the series again in 2024. My name is Lauren Linsmeyer, and I'm a Senior Science Officer with the California Ocean Science Trust, an independent nonprofit that bridges the gap between cutting-edge research and sound ocean management in California. I'm joined today by my co-hosts, and if we could go to the next slide, please. We have with us today, and with this series, Darcy Dugan with the Alaska Ocean Observing System and the Alaska Ocean Acidification Network, Alex Harper with the California Current Acidification Network and Central and Northern California Ocean Observing System. Supporting the webinar series this year, we also have Alexandra Puritz with NOAA's Ocean Acidification Program and the National Coastal Acidification Network, and Kevin Travis with the California Ocean Science Trust, who's making sure this webinar is running smoothly today. Next slide, please. So together we're working to create a dialogue among industry members, tribes, natural resource managers, and scientists throughout the West Coast and Alaska to provide a better understanding of marine carbon removal technologies, state of the science, and ways to become engaged in this field. During today's webinar, attendees will be in listen-only mode. You can type questions into the Q&A function at the bottom of your Zoom screen, and we will pose those to the speakers after their presentation. We will also do a few poll questions throughout to help inform this series, and we are recording this session and we'll share that recording on YouTube after. The title of today's session is A Look at ARPA-E Programs to Support Measurement, Reporting, and Validation of Marine Carbon Dioxide Removal. We'll get started here with our speakers in just a minute after I introduce them. So we have Dr. Simon Freeman, Program Director, and Dan Rogers, Technology to Market Advisor from ARPA-E, or the Advanced Research Projects Agency Energy within the U.S. Department of Energy. And they will be sharing with us about 2 programs, the CCO2 and Mariner programs, that are supporting the development of technologies to validate marine CDR effectiveness and monitor impacts. So we're looking forward to learning more about these federal programs, the projects being funded, and the value of robust MRV. So we have about an hour for today's webinar with Simon and Dan presenting, followed by a moderated Q&A at the end. And before we start, we would like to ask a poll question to get a sense of the audience's familiarity with ARPA-E's programs prior to this webinar. Actually, you can ignore this QR code for right now, and we will start the poll in just a second. Wonderful, here it is. So have you heard of ARPA-E's programs funding marine CDR prior to this webinar? We'll wait just a few more seconds for folks to answer. Okay, think we can close the poll in a few seconds. Wonderful. Thanks so much. It looks like we have a lot of people learning about ARPA-E for the first time. Great. So before we hand it over, I would like to give a little bit more introduction to Simon and Dan. So as I mentioned, Dr. Simon Freeman is a program director at ARPA-E, where he focuses on maritime energy and environmental sensing technologies. Simon previously worked as a civilian oceanographer for the U.S. Naval Research Laboratory and the Naval Undersea Warfare Center Division Newport, leading the development of technologies and methods for underwater vehicle and sensor design, acoustic sensing, and seabed access. He earned a PhD in oceanography from Scripps Institution of Oceanography. Dan Rogers is a tech-to-market advisor at ARPA-E, where he focuses on transformative, high-impact marine technologies. Dan previously worked as a remotely operated vehicle pilot and mechanical engineer, including for NOAA ship Okeanos Explorer. He also worked at the Consortium for Ocean Leadership in DC, working across industry, government, and academic institutions to capitalize on shared priorities and advance community-wide goals for ocean science, data, and technology. He has an MS in mechanical engineering and an MBA from the University of Massachusetts Dartmouth. So Simon, I will now pass it over to you for your presentation.
Thank you very much, Lauren, and it's a pleasure to be here, everybody. We appreciate your time, and we're very excited to share a little more about ARPA-E and what we're doing in the ocean energy space. So let me just share my presentation. Okay, let me know if that's not coming through. All right, there we go. Let me just switch this. Hang on for one moment. I think I've got the wrong screen going on. Start again. Yeah. Okay. There we go. There we go. Okay. So we're going to speak today about mainly about our new program at ARPA-E known as CCO2, Sensing Exports of Anthropogenic Carbon Through Ocean Observation. It's an ARPA-E program to support measurement, reporting, and validation technology development for supporting the marine carbon dioxide removal industry. So my name's Simon Freeman. I'm a program director here at ARPA-E, and then Dan Rogers will be speaking with me. He's a technology to market advisor. So before I begin, though, I just wanted to plug something that we're doing at our agency next week. The American Geophysical Union Ocean Sciences meeting is taking place in New Orleans. This is the first time that meeting is occurring in person in, I think, 6 years, just because the last two were either canceled or virtual due to COVID. So ARPA-E is there giving a town hall on Tuesday. We have an exhibit booth, and also I'll be speaking more about the CCO2 program. So please, if you're visiting that conference, feel free to drop by. You're more than welcome to speak to us. And another plug here for our annual summit. So ARPA-E has an in-person Energy Innovation Summit once a year. And of course, we're happy to answer questions about this, or you can visit the website that's listed down below there. So I want to speak a little about ARPA-E. I know that this agency is new to the majority of you. We are part of the Department of Energy, and we're a funding agency, but we're different in that we subscribe to the ARPA model, the Advanced Research Projects Agency model that was pioneered by the Defense Advanced Research Projects Agency, or DARPA, starting in the late 50s. So the idea is to bring about transformative leaps in technology through high-risk, high-reward projects. And ARPA-E's mission areas are not defense-related, they're energy-related, and they focus on 5 things. So reducing imports of energy commodities, improving efficiency, reducing emissions, including historical emissions. This is an important point here, because it's only recent that ARPA-E has started to expressly address climate change. improve the management of radioactive waste, and improve grid resilience. The thing that we do, which is quite unique to other funding agencies, is we fund this high-risk, high-reward transformative research with the goal of creating disruptive technology. So if you imagine that yellow line shows the curve of existing technology, the costs reduce with increasing scale and time, but could we develop something that is breakthrough, that could be very expensive initially, but would dive below that existing technology curve to disrupt energy industries? So that's the goal of ARPA-E. We found this really nice figure from Extantia online about the critics that we do. This figure showed MLIL, technology readiness thing, which is a scaled market at TRL9. And ARPA-E really funds very, very nascent science, grants and science risk, pre-seed to something around the seed or engineering risk scale. And we have a number of grant mechanisms or award mechanisms by which we fund things in this way. But as Dan will talk about soon, it's not just a science project that we fund. It's something that is intended to become commercialized and become the sort of scaled kiloton and megawatt industry of the future. So this is a high-level view of how we think about the ocean. And we updated this slide very recently. On December 22nd, the State Department submitted a claim with the UN to include the outer continental shelf of the United States in our exclusive economic zone. And roughly, that area is shown in purple in this map. And of course, the part north of Alaska looks enormous because of Mercator projection. But what this has done is if it is successful, is that it will increase the size of our maritime exclusive economic zone to the largest in the world, 12.5 million square kilometers. And if you compare that with near peer or peer states, such as China, the amount of ocean area we have is incomparable, and none of our ocean area is contested. So this is a tremendous, tremendous advantage that we hold, yet we utilize this area for very little. Commercial fishing, maybe some for offshore wind, etc. There's so much more we could do with our ocean exclusive economic zone for energy and climate purposes. So along those lines, we started at ARPA-E this program, Mariner. Mariner stands for Macroalgae Research Inspiring Novel Energy Resources. This program was started by my predecessor, Dr. Mark von Keitz, who now works at the Grantham Foundation, in 2016. And ARPA-E attempted to build, or is attempting to build, a US marine algal biomass industry from zero. So back in 2016, no seaweed was farmed in the United States. We now have a market of roughly 440 tons per year, nothing compared to, or almost nothing compared to, say, Korea with a 1.8 million ton per year harvest. But we're growing this in an effort to create new sources of renewable hydrocarbons for energy as well as food, but other energy relevant industries such as fertilizer or animal feedstocks and so on. So the idea, and we should update this, it should be the world's largest EEZ. We should use this to our advantage. One quick example of how ARPA-E works is this example of our flexibility. So the images on the right show a CGI render and a photograph of the work done by a company named Captura. And Captura are based in Los Angeles at the port of LA, and they've spun out of Caltech. Harry Atwater was the PI there. Captura are an electrochemical carbon removal company. So they're removing CO2 from seawater, de-acidifying it, and capturing the CO2 to reduce the amount of atmospheric CO2 in the atmosphere. We gave them $500,000 worth of seed funding for their electrochemical stripping unit and the pH swing system that draws CO2 out of seawater. They leveraged that for a $16 million Series A funding round. The provenance of ARPA-E is strong in the investor community, and they leveraged the confidence that we instilled, we have in them to obtain this further funding. Now they're scaling to a 1,000-ton facility in Norway. However, despite giving them $500 million, they worked on their project for a year or so. Then we plussed them up by more than the initial award amount, $650,000. We gave that to them to perform a numerical study on effluent dynamics. What happens to decarbonize seawater as it is pumped back into the ocean? I mean, it's otherwise clean, but how does it mix? And more importantly, what are the ecosystem impacts of that water? Could this water, which was clean but had higher pH, positively influence the ecosystem, positively influence these commercially relevant species in Southern California: oysters, mussels, sea urchins, and also kelp? The idea here was to investigate the idea of creating positive social license with carbon capture, as well as realizing total carbon credit value by accurately tracking the carbon drawdown that comes about through the effluent in seawater. So these are things that would never have been funded by venture capital because they don't immediately pad the bottom line, but they're important for things like ultimate social acceptance. So starting to move towards the program CCO2, I wanted to talk a little about how ARPA-E considers the ocean and the climate. So on the left is a figure from the UN Environmental Program. It was created in 2017, and it shows there's a graph there that shows how we will maintain a global temperature, global warming below 2 degrees Celsius. And on the vertical axis is a gigaton value per year of emissions, gigatons of CO2 equivalent. And on the horizontal axis is time out to 2100. So in 2017, the UN surmised that sometime around 2020, we would rapidly swing away from business as usual and turn to rapid decarbonization through conventional abatement, that's like wind and solar and nuclear, and then capture of carbon from emitting technologies like scrubbing, smokestacks, etc. And we would maintain this I'll track along this red line to remain below 2 degrees Celsius of warming. However, the blue area below the zero, the horizontal axis, is what interested us. That represents the negative carbon industry. Carbon capture must occur on the scale of 10 gigatons per year by 2050 and 20 gigatons per year by 2100 or thereabouts to enable us to remain below 2 degrees Celsius of warming. Now, in 2024, this figure would look, the blue area would be larger than this, right? Because emissions have continued to rise year over year. But the point for us is how is this carbon going to be captured, and where is it going to be stored? If you look at the figure on the right, that shows a scaled image of the Earth from the perspective of the Cook Islands. You can see that it's mostly water, 71% of the surface of the Earth, 71% of the insolation, that's the amount of energy from the sun that arrives on the Earth, arrives on the sea. So we felt that it's rational to think that most carbon dioxide removal and carbon storage would happen at sea. If you look at this report, the Negative Emissions Technologies and Reliable Sequestration Report issued by the National Academies of Science in 2019, they consider all terrestrial and coastal carbon sequestration, carbon capture technologies, and maximum safe limits of these technologies. They show that these technologies are not going to be enough because at maximum safe levels, they would sequester roughly 10 to roughly 11 gigatons of carbon per year. And we don't know if, say, forest management is going to be permanent enough to bring about the substantial changes in greenhouse gas concentration in the atmosphere required to maintain warming below 2 degrees. So we need something bigger than just terrestrial carbon removal. Looking at the ocean, this is a slightly dated figure, but the numbers are still relevant. This is from the IPCC in 2001. Ocean carbon cycles are enormous. Roughly 100 gigatons of CO2 is absorbed by the ocean every year. Now, about that amount is released by the ocean as well, but the smaller arrows in this figure matter. Roughly 10 gigatons of carbon per year are transported from the surface to the deep ocean, where 38,100 gigatons of carbon is stored. That's not in sediment, that's in the water. And even a 1% change of that number could mean significant implications for our climate. So there are marine carbon dioxide removal methods that intend to increase these numbers of downwelling carbon or flux towards the deep ocean or seafloor. These could mean a lot for our future climate. And this report, another report by the National Academies in 2021, I think, December 2021, Ocean-Based Carbon Dioxide Removal and Sequestration, a research strategy, outlines 6 major methods of carbon capture and storage in the ocean, both with synthetic methods and natural, including ecosystem restoration. But if you read the report, it shows that in almost every case, there is significant uncertainty when determining the efficacy, the effectiveness, the additional impacts of each of these techniques. There's a lot that we have to learn about these and their effectiveness. So that's why we decided to launch this program, CCO2, where we're trying to create viable measurement, reporting, and validation technology for marine carbon dioxide removal processes. So imagine in the future, you have an industry where folks run these ocean carbon dioxide removal mechanisms, whatever they look like. And there's a little icon in the left side of that loop there that shows some sort of machine capturing carbon. Those or to folks looking at atmospheric carbon dioxide. And then in turn, they would be paid. But a critical issue here regarding how much they would be paid is they would need to know how successful the carbon capture technologies were. How can they validate how much carbon was drawn down at the ocean, and how long will it be stored under the ocean? So the program scope of CCO2 is given there by this the dashed line, and the technical areas involve developing a new generation of ocean chemical sensing tools that sense at scale, volumetric over kilometer scales rather than point measurements. And then secondly, to create effective models that estimate carbon dioxide removal performance using this new type of data. And the rationale here is that this quantification is essential to give carbon dioxide removal financial value in a carbon market. And as I mentioned before, the ocean promises the biggest scale with the least adverse impact to reversing our existential climate disaster. So to date, we've invested $37.3 million in 11 teams, and that number will only go up in the future. So, the way that we see this is that we face a decision at ARPA-E and also globally. We could choose between a future that looks like the one on the left, credit to Blade Runner, and the one on the right, which of course is an AI-generated image, but I hope it gives you a good impression of what we're talking about. We want to try to develop technologies that push us to the right there. And as such, CCO2 it's more than just a science program. We want to enable the scaled reversal of climate change in the fastest and most scalable way possible. And as such, ARPA-E, while we provide funding, we're more than that. ARPA-E offers support to achieve these goals. So the management of ARPA-E projects is active. There are quarterly reviews. The program manager comes on site. There's technical guidance from a team of PhDs at ARPA-E. We offer networking and communication, and as well as follow-on opportunities, such as the summit I talked to you about previously, where folks are given an opportunity to pitch to investors, for example, and network with philanthropy, etc. So there's another piece here too to this puzzle, which is that while carbon capture reduces emissions, including historical emissions, there's an important component here about improving efficiency. Assuming that we're going to sequester 10 gigatons per year in 2050, the energy cost to do that is going to be colossal. And assuming we sequester 10 gigatons with direct air capture, which is something that is $1.2 billion worth of tax credits in the IRA for direct air capture, we're going to need 20,000 terawatt hours of electricity. That's, I think, 2,000 terawatt hours is more than it's far more than what the United States uses per annum for our electricity needs. So the scale is enormous. Conversely, if you look at the marine carbon dioxide removal methods that I talked about previously, these are just estimates, but the amount of energy required to draw down a gigaton of CO2 is potentially far less. In some cases, such as an ecosystem restoration, assuming you could find the scale, it costs you no energy. So there's an energy efficiency play here as well. So when forming the thesis for CCO2, we looked at the scale limits of present-day carbon sensing approaches. And on this stylized image, we show logarithmic time scale, and then on the horizontal axis, and spatial scale on the vertical. And we plotted approximately what the spatial and time scales of various sampling approaches would be today. And you can see that, while, say, sediment cores give you a wonderful time series of sediment deposition, they only give you spatial resolution that's a spatial capability that's very local. One could use an autonomous underwater vehicle to survey square kilometers, but they quickly run out of batteries. So we felt that there was a really nice white space there for transformative sensor and modeling technology, where we would look at spatial scales commensurate with regional carbon dioxide removal efforts that would need to play out over multiple years. So this is quite a wordy slide, but these metrics are clearly outlined in our funding opportunity announcement, which is no longer open, but it's still on our website. I want to draw your attention to the most important metric, metric 1, and ARPA-E programs, I should mention, define themselves by program metrics. What goals, technical goals, are we trying to achieve? And this one is aspirational. We calculated, based on a number of examples of carbon dioxide removal efforts that are being proposed in the ocean, that in order to conduct effective measurement reporting and validation, one would need to survey 150 cubic kilometers of ocean per hour. That's new water per hour to perform adequate validation of a gigaton of CO2 per year drawdown. So that kind of scale is enormous. But when we think about how much money one would have to do this, typically MRV costs about 5% of the total expense of CO2 drawn down. That's in terrestrial CDR. At $100 a ton, 1 gigaton is $100 billion. So you'd have $5 billion to do this. So not only is the scale of the area large, the scale of the financial resources is also going to be very large. So there are some other metrics here, including the accuracy of sensors. They do not need to be over and above what we have today, but they need to be scalable in terms of volume. Sensors must fit on a commercially off-the-shelf platform, a commercially available off-the-shelf platform. They must last for a year in the ocean without human intervention. And then climate models that estimate carbon dioxide removal drawdown need to be accurate to something comparable with state-of-the-art today. So in summary, CCO2 creates technology that allows accurate quantification of CO2 removal to give carbon dioxide removal in the ocean financial value in carbon markets. And we think the ocean offers the biggest scale. And there's a figure here on the bottom of this slide that shows, today we have this paradigm of chemical oceanography, where you have physical collection of water, you have point sampling systems like those sediment traps there. We want to go from that to sensors that are volumetric or area-based, maybe focusing on electromagnetic, optical, and acoustic methods, and those would provide the data for a new generation of data-driven models. And ultimately, that would mean more accurate estimates of carbon drawn down and high quality credits, because the credit value is now verifiable. So I want to talk a little about the types of technology that we funded. Here, this is just an overview of what we need in terms of sensor development. So we need a paradigm shift in ocean chemical sensing from sensors that look inwards to outward-looking, volumetric. They also need to come down in price significantly. They need to be more reliable and offer volumetric access. So I've got a few examples of some of the teams that we have funded. So first, I should mention all of these teams are still under negotiation. So the program is about to kick off, and it'll be a little while until you see results, but I'm sure you'll hear about them perhaps in a future seminar. This is a project by General Electric. They're leading a consortium of folks, including researchers at University of Rhode Island and Ebb Carbon. They want to create a distributed chemical fiber sensing system. So today, one can use distributed fiber to sense vibration and temperature through the interaction of these parameters with an optical fiber and the light pulses that are sent down the fiber. These folks think that they could add a chemical cladding to the outside of the fiber that mechanically responds to changes in pH or the partial pressure of CO2 and seawater. And that would mean that the optical transmission in the fiber changes ever so slightly. And by time gating the pulse returns, they can determine where along the fiber the pH or PCO2 is changing. So the dream is to do this in the ocean, much as they do today with acoustics or temperature. And if they were able to tow such a system through the ocean, they would create a volumetric measurement at the kilometer scale or cubic kilometer scale with distributed chemical sensing. The next project I want to briefly touch on is this one here. The PI is at Woods Hole Oceanographic, and they're working with University of Michigan, University of Pennsylvania, and a company, Analog Devices. And they've looked at the Argo situation. Argo, it's the global network of autonomous floats that every 2 weeks, each float will profile from 2,000 meters to the surface, taking oceanographic measurements. A subset of Argo are the biogeochemical Argo systems that take a number of other measurements, including pH and PCO2, oxygen, nitrates, etc. These systems are very expensive right now, about $100,000 each. These folks want to take all of these sensors on a BGC Argo and miniaturize them and put them on a single chip. And Analog Devices is one of these sort of chip manufacturers, right? By reducing the size and the form factor, they hope to reduce the energy consumption and significantly the costs, down from about $60,000 for the sensor suite on a BGC Argo to maybe several $1,000s. And the system would be very small. It would be easy to mount on an Argo or something else, and they could potentially revolutionize the ability that we have to sense distributed chemical oceanographic parameters on a global scale. The last one I wanted to talk about is a really interesting project from the University of Texas at Austin. These folks have been working on an NSF grant over the last few years to look at ecology in seagrass beds using acoustics. And now they're turning to looking at the carbon flux in a seagrass bed. So it turns out that seagrass is very effective at drawing carbon down from the surface ocean. And once that carbon is stored in their root systems and in organic material under the sea floor, so long as the material remains in an anoxic environment, that carbon can be stored for thousands of years. But the rate of seagrass-based carbon drawdown and the success and permanence of carbon storage under seagrass beds is difficult to determine. These folks think they can do this acoustically. Firstly, as seagrass photosynthesizes, excess oxygen forms bubbles on the leaf surface, and they make sound. So one could determine quantitatively what the photosynthesis rate may be from just listening to the bubbles. So that is one way to determine net ecosystem productivity. The second thing that they would like to do with that sound is to perform geoacoustic conversion using ambient noise. That is to say something about the sediment properties by looking at how sound is modified as the sound refracts through the sediment. This is something that is usually done to search for, say, oil and gas deposits in the deep ocean. These folks want to do this at a very small scale with higher frequencies underneath seagrass beds. There on the lower left, there's a figure that shows a temporal match between the amount of photosynthetically available radiation, or PAR, and then the sound level of ambient noise produced by a seagrass bed. And that shows you that the photosynthesis drives the sound level, ambient noise level on the seagrass bed. The other part of CCO2 involves the creation of transformative MRV models for carbon dioxide removal. We think that in the future, MRV is going to be conducted much as weather is predicted today. Models evaluate what's going to happen, and perhaps there may be some validation measurements, but they're relatively few in number. We think that with the volumetric sensing and transformational technologies that we would develop under CCO2, we would be able to create very large quantities of quantitative data that could then be fed into new models that would bring about an improvement in model skill, much as they did with, this is a historical plot on the right that shows skill improvements from the European Center for Medium Range Weather Forecasting. And these different colors represent variables in models. The vertical axis represents the skill, and the horizontal represents time. It's over about 30 years. And sometime around the middle of the figure, that's around the year 2000, you see a dramatic decrease in the variability of each parameter and an increase in the accuracy. And that was due to the introduction of new digital satellite data around the year 2000 that led to significantly improved medium range weather forecast models. So that's a precedent there that we want to try to emulate with CCO2. And the users of such models aren't going to be the general public. They're going to be groups like carbon registries or carbon marketplaces. And there are a few examples down the bottom there, who could really benefit from these types of improved models of carbon dioxide removal efficacy. So the dream that we have is to create figures like the one on the left. This is a satellite-derived image of chlorophyll A in the Gulf of Mexico, but do this without satellites. And the figure on the right shows a NOAA ship scanning the sea floor with a multi-beam sonar. Imagine rather than sound, we're picking up this kind of information regarding carbon flux. We're not saying that these things are possible, but these are the kinds of dreams that we have, that the things that we want to try to achieve at ARPA-E. So with that, I'll finish on this slogan. This is ARPA-E's mantra. If it works, will it matter? I've spoken more about things that may or may not work in the future. And Dan Rogers is now going to come on, and he's going to speak about the other aspect of ARPA-E, technology to market. If it does work, will it actually matter? Thanks a lot.
Thanks, Simon. And actually, if you want to stop screen sharing, it might be easier if I pull up my screen at this point. All right. Yeah, so hi, everyone. So again, I'm Dan Rogers, Technology to Market Advisor for the Marine Technology Portfolio at ARPA-E. And as Simon mentioned, we have this slogan at the agency, if it works, will it matter? If it works is really focused on the technical advancement and all the ideas that Simon has been talking about in terms of CCO2. However, if those technologies work, if those transformative approaches work, how will it matter? What impact will it have? And that's the role of technology to market at the agency. And the commercialization technology to market focus of ARPA-E is reflected in what we call the impact indicators, which you see here. These are the metrics by which we adjudicate our own success internally and the metrics that we report back to Congress and the administration to show that we're using taxpayer money responsibly and appropriately. And these are things like the number of patents secured by our teams, the number of licenses they issue, the amount of companies or startups spun out of ARPA-E projects, and the amount of follow-on investment by both private investors as well as other government agencies. And so I think what this gives you a sense of is how commercialization and tech to market is really a critical component of ARPA-E projects that we fund. Now, we don't expect teams to do this on their own. And so we do provide both funding and resources, as well as coaching, guidance, and expertise to help our teams be successful in their technology to market efforts. And so what you see here is a very conceptual graph of what we see as the tech to market effort intensity over the typical 3-year lifetime of an ARPA-E project. As you can see in the beginning, we have a lot of effort as the teams come up with their commercialization hypotheses and write up tech to market plans and start to think about how their technology will have impact in later years. And we do have a unique requirement at the agency, and that's that at least 5% of the overall project budget has to be dedicated to going to technology transfer and outreach, commercialization, tech to market activities. And so that's a baseline from which teams are operating. And this can go to things like, just the time it takes to develop a commercialization plan. You can use that to, attend conferences and advertise your technology. You can hire an external consultant to help you with financial modeling for a potential company. So it's a pretty broad array of activities that this funding can support. Of course, the middle years are mostly focused on technical advancement, though there is some consistent tech to market effort. But it really ramps up again towards the end of the project, towards the end of year 3. And at this point, depending on technical success of a project and commercialization effort, we can actually provide additional tech to market funding of up to $300,000 for more focused tech to market activities. And we have a number of teams that do take advantage of this to help them be successful. And once an ARPA-E project wraps up, teams are then eligible for our scale-up program. This typically happens every 2 years. The last solicitation was in 2023. So you can do the math and figure out when the next one might happen. But this is an entirely separate ARPA-E program for which teams that have already finished up their projects can apply for additional funding in the millions to tens of millions of dollars to help bring their technology from proof of concept, from pilot stage to commercially scalable and deployable systems. So that's been a really successful program at the agency. So what does this mean for CCO2 specifically in terms of our impact? Well, we see the impact happening in 3 phases for this program. And the first and most near-term and important element of the program is to either validate or invalidate these new MRV approaches in both sensing and modeling, as well as determining the validity of marine CDR efficacy across the different engineered approaches that Simon discussed previously. So in order to do this, we're going to be partnering with other government agencies, with NGOs, and helping bring our MRV funded technologies to potential pilot projects that other groups are working on to validate both. Now, in the medium term, should some of these marine CDR approaches prove viable, there's a number of things that we see occurring in parallel that CCO2 can help support and help potentially accelerate adoption of marine CDR as an industry if appropriate. And these are things like informing carbon market protocols by working with carbon market entities, carbon registries, and other carbon market experts. We also want our teams to be engaging with both federal and state regulatory bodies to help inform policy and regulation frameworks. And one key application that we see coming from these technologies is to support ocean observing and monitoring. These tools can be used to collect baseline information to inform academic and government research, fill information gaps, and of course, collect information about the baseline natural carbon fluxes for which future engineered marine CDR projects will be measured in the future. And ocean observing obviously is a more near-term market than the highly uncertain marine CDR industry. And so we do see, upon success in the next few years of these new sensing capabilities, our teams working closely with ocean observing communities going forward. And of course, the long-term impact and sustained impact that we're hoping to have is to, as Simon mentioned, provide confidence in carbon removals in both the voluntary carbon market as well as potential future mandatory compliance carbon markets. Just in terms of the voluntary carbon market, this is an existing mechanism through which carbon removals can be made profitable for a private company. And so we see this as a very near-term opportunity for commercialization. This graph, what you see, the black bars for both 2030 and 2050 are based on the gigatons of carbon removal per year based on current commitments by over 700 industrial entities around the world. However, in order to stay within our 1.5 to 2 degree warming pathway, the blue bars on the right are the amount of removals that we need to be seeing on an annual basis by those years. And you can see that just out of necessity to hit climate targets, we're anticipating pretty tremendous growth in the voluntary carbon market in the coming years, in the coming decades. One estimate by McKinsey recently estimated that the voluntary carbon market may be worth 30 to 50 billion by 2030. It's not very far away. And again, if MRV is just 5% of that market, that's a $1.5 to $2.5 billion market just for the monitoring aspect of marine CDR. If marine CDR is a significant component of the VCM at that point. So a key challenge to scaling the voluntary carbon market, as you can see on the chart on the right, taken from a survey of carbon market entities, are the quality of carbon credits and dealing with carbon accounting uncertainties. So this is a key challenge that our MRV technology is hoping to solve. Providing the tools to help assess measurability, quantifying the amount of CO2 removed, verifiability, how can you actually validate by third party how much CO2 has been sequestered, the durability. If you draw down carbon in one part of the ocean, how long does it stay there before it actually gets re-emitted in another part of the ocean later on? And of course, assessing additionality from baselines, as I mentioned, from those natural carbon fluxes that are already present on the gigaton scale. And so these are the key challenges that our MRV technologies coming out from our project teams can help address. So we have 11 teams, all considering very different commercialization models. I'll just note that the logos on this slide are just for illustrative purposes and don't actually reflect any actual agreements or partnerships at this point. But we do have a number of teams pursuing a direct sale model where they may develop a new hardware or sensing capability and partner with a platform developer and maybe an oceanographic sensing developer in order to create new systems that they can provide directly to those who might use it for MRV purposes. Many of our teams are considering a licensing model where they want to develop new IP over the course of the project and then license that IP out to existing established oceanographic sensing companies that can then provide those tools to the market. And we do have a limited number of teams that are looking at a data as a service model where they'll actually utilize both hardware and software and modeling in order to provide end-to-end MRV solutions and help serve this application. So again, although our primary use case is marine CDR, MRV, these are also valid commercialization approaches for serving the ocean observing industry as well. So I just want to go ahead and wrap up by reiterating what Simon had mentioned at the beginning. We're going to be at Ocean Science next week, first time that ARPA-E has been at that conference, and we're excited to host a town hall next week, Tuesday, from 12:45 to 1:45 Central Time, as well as a session on CCO2, and we will also have a exhibit booth. So we look forward to meeting many of you there. So I'm going to go ahead and wrap it up there, and thank you for your time. And Simon and I are looking forward to any questions that you might have about the program. Thank you.
Thanks so much, Dan and Simon, for those really fantastic presentations. It was really interesting learning about some of the newly funded projects and the services through ARPA-E. So before we get to some questions, we wanted to do another quick poll. And so we're going to have people use Wordle, or not Wordle, word cloud to describe in one word how you would describe marine CDR. And so, yeah, Alex Puritz is going to share her screen, and we're going to have share a link that you can follow to add this word. It's up here. It says menti.com, and there's a code as well. And we have that in the chat too. Great. So as people are entering their one word to describe marine CDR, Alex, maybe you can head over to the other tab to show the word cloud as it's being created.
Do you see the word cloud?
Yes.
Great.
Thank you. See several words popping up. Wonderful. Great. So as that is happening and unfolding, feel free to also add more questions into the Q&A box. Great. Maybe as this is as people are adding the words. And I see uncertain is definitely the biggest right now. We have old, scalable, expensive, multifaceted, promising. This is really fascinating to see people's thoughts. Great. I think we can share the final word cloud, but in the essence of time, let's move on to the Q&A. So you can stop sharing your screen. Great, thanks. Alrighty. So there was, starting out, there was a question in the chat about the issue of dilution in the ocean. And I'm wondering if you wouldn't mind, I think that one's really interesting and pertinent here for the sensor development, Simon. So if you could answer that again. And the question was around, given that any chemical signal from a marine CDR project is likely going to very quickly be diluted, given the ocean, below any limit of detection of even current state-of-the-art lab-based sensors, what aspect of these new sensors gives us confidence that they can overcome this problem and detect the signal out of the noise?
Thanks. Yeah, so this is a great question. I think a couple of people have asked variations of this in the chat. And I tried to answer with a written response, but just in summary, we realize that this is a big challenge. And not only does the signal of a CDR plume, let's say an alkalinity plume from an alkalinity enhancement experiment, and not only does the signal become exponentially smaller with distance, it spreads in area, right? So you have this simultaneous issue where you have to measure a far larger area at a higher precision in order to track a plume. And this is very difficult. So, in the short term, what we hope will happen with CCO2 is this direct connection between sensitivity and value. So if one is able to objectively measure a plume at a higher level of sensitivity, one would be able to claim a larger carbon credit because you could objectively show that the plume was bigger than what one could quantify with a less sensitive sensor. So there's an economic driver for increased sensitivity, which is potentially really great. But the second thing is, eventually it's going to be not cost effective to quantify such a plume. And we think that at the end of the day, MRV is going to largely be conducted through modeling, and that models would create estimates of how much carbon was drawn down. They would be validated with some environmental measurements. The accuracy of the models is paramount. And so understanding gradients and understanding interactions with biology, I think, is the best way to go about getting to a realistic solution there.
Great. Thanks, Simon. All right. I think for our next question, we are going to ask about, this program, CCO2, is very focused on MRV, but for the techniques to be, or for marine CDR, but for the techniques to be deployed, it'll be critical for environmental MRV to establish their social acceptability. So are there any plans for ARPA-E to help address that?
So we considered this really carefully during our program development workshop. And at the time, the term eMRV was not, had not been coined yet, right? So we talked about environmental impacts. And really, given limited time and funding, we figured we would go with the following. What is the one monetizable value in carbon dioxide removal? And that's carbon, right? How much carbon have you drawn down? We realized that there are a lot of other important questions associated with that, but we figured that unless you are able to quantitatively determine the market potential of a technology, it would never occur anyway, right? So the first step would be to show, hey, this could earn a lot of money, or this could really draw down carbon efficiently. Then we would think the next step would be to look at eMRV. Now, while programmatically we're focused on the carbon. Realistically, the sensors that we're developing would very much assist with understanding environmental impacts or even EMRV. I note that some of them include the sensing of the ability to sense dissolved organic carbon and also particulate organic carbon. These are very closely related to biological processes. So we're hoping that we assist in all fronts, but the program is designed to look at carbon value.
Great. I think we have time for maybe one more question before having to start to wrap things up. So phase 2 of CCO2 talks about bringing sensing and modeling efforts together. What might this look like, and what can we expect in terms of feedback and interaction between the two groups working on sensors and improving models?
Yeah, so the intention has always been to combine sensor developers with model developers and provide, real world data from these new sensors. And firstly to benchmark and then to assist in data-driven model development. Of course, when we issued the public funding announcement, we were beholden to what types of responses we got for specific sort of regional modeling and sensor development efforts. So in some cases, we have some teams working on alkalinity enhancement and modeling for alkalinity enhancement. We'll definitely have these folks work together. But in other cases, like the seagrass folks, nobody is modeling seagrass carbon, at least in our portfolio. So the way forward is probably going to be working with the team to identify potential collaborators. These teams, as I mentioned earlier in the presentation, we allow for dynamic funding at ARPA-E. So they would, if they achieve good technical results with their sensors, we could potentially plus these teams up as they bring on another co-investigator to work on modeling. The last point is that we have seen a lot of interest in the philanthropic world and other federal agencies like NOAA funding carbon dioxide removal work. We're hoping to try to leverage some of these organizations or some of these programs more formally in the future. And we imagine something like a joint effort where ARPA-E may partially fund work that is collaborative with these other groups. So at the moment, I mean, we're really playing things by ear. Of course, there's no guarantee that our modeling and sensor teams are going to achieve success, and it's going to be constant. We're going to constantly evaluate how we can put the modeling and sensor teams together to bring about these sort of more viable outcomes. Thanks.
Thanks, Simon. And as we start to wrap up here, was there any final things either of you wanted to share? I think we covered a lot of great ground. And Dan?
Yeah, just want to thank you, Lauren, for helping to organize this, and thank the California Ocean Science Trust and your partners for helping us spread the word about CCO2. We're really excited about kicking the projects and the program off in the coming months, and we look forward to providing updates on the successes in the future.
Likewise, thank you. This is a great opportunity for our audience.
Thank you very much to the California Ocean Science Trust, and thank you very much, Lauren, too, for giving us this opportunity. Of course, maybe I'll just mention, if you have any other questions, we'll be at Ocean Science meeting next week. Please, we're more than welcome to approach us at our booth or at our town hall, or if you just see us around, and we'll be more than happy to discuss with you.
Great, thank you so much, both. And as we close, we have 2 more really quick poll questions if folks would be willing to stay on and answer those to help inform the rest of this webinar series. So with that, we have our next question about the format of these webinars. If you like the mix of presentation and Q&A or would prefer more of one or the other. Okay. I think we have pretty good participation on that one, so thank you all so much. And then one more really quick one, feel free to follow up with us as well. It's about if you have any ideas for future webinar topics on marine CDR, or ocean carbon, or have other speaker suggestions. Also, feel free to reach out to us after this. We welcome any future ideas. So with that, I think I'm going to end this poll. And thank you all again. Thanks so much to Simon and Dan, to our other co-hosts, and to all of you for joining. Again, a recording of this webinar will be shared on YouTube and our websites in the coming weeks. And I hope everyone has a great rest of the day, and see many of you at Ocean Sciences next week.